Welcome to this afternoon's CLSP seminar. We're very pleased today to have as our speaker Shimon Edelman of the Department of Psychology at Cornell University. Professor Edelman has done lots of important work in the area of human vision, and his work has been extremely interesting in trying to integrate insights both from neuroscience and studies of human vision, as well as results from computer vision. In the last couple of years, he's turned his attention from visual perception and visual representation to issues concerning language, and has tried to apply some of the same insights, ways of thinking about learning of visual structure to learning of the structure of natural language, and today he'll tell us something about that. So thank you for coming.
Thanks very much for inviting me. It's fun to be here. It's my second time. I gave a colloquium here 2.5 years ago in the Krieger Institute on visual neuroscience, in fact. And if we move into language, I'm told that this is a standard way of introducing the big problem, the problem of inferring grammar from experience, from examples. So we have experience, and then we have something, an intervening process, and then an internal representation of language. And this is what we are told as recently as this year, in fact, in one of the interviews with Chomsky published. This is what he tells us. In structuralist linguistics, the idea was that, notice the past tense, the idea was that you did it procedurally. That plainly didn't work. You get the phones and the phonemes and the morphemes, and it just gets nowhere. So I want to show you some evidence that one can actually get a bit farther than that, beyond the morphemes, to structures that are, I'm not being facetious here, it's a difficult undertaking, but one can get much farther from just the morphemes. One can get to some structures that certainly look like they have some linguistic relevance, and that also can support all kinds of interesting behavior. For example, the set of representations that we extract, that the algorithm I'm going to describe extracts, withstands some standard tests, for example, English as second language test. So the project is a joint undertaking with some people in Tel Aviv. The person showing in red here, Zach Solan, is the graduate student responsible for it. Wonderful person to work with. And my two colleagues in Tel Aviv on the faculty of Tel Aviv University, David Horn and Dayton Rupin. And we call the project Learning of Natural Languages because it happens also to apply. The algorithm happens to be pretty effective in finding structure in DNA sequences and in protein data. But that's something completely different. I'm not going to touch that topic at all. But that's the source of the plural here. And in some sense, DNA is a natural language. So we start with a data structure that looks like this. It's a lexicon, just the unique words in what you'd call a lexicon, augmented with two special symbols, begin and the more sentences you adduce to a corpus, the more paths you have through this graph. So here, one sentence could be begin implicitly, is that a cat? Question mark. And another sentence could be, is that a dog? And so on and so forth. And it looks like a mess if you look at things this way. So here's this big graph, as big actually, the number of nodes, vertices would be the same as the number of words in your lexicon initially. Although, as I hope I remember to mention later, we can also start with units that are smaller than what you'd call words. We can start with a run-on sequence of a text from which we omitted all the spaces, and it bootstraps itself. But intuitively, it's easy to think about things in this manner, but of course it looks like a mess. And to find order in this mess, we employ a technique that has been known for a long time, essentially since Zelig Harris's work, alignment, looking for distributional equivalences, but with a twist, actually, with several twists that makes this work, that make together this work and take it beyond this capability of finding, as Chomsky claimed, mere phonemes or morphemes. So if you take the different paths in that graph and you try to align them, you find commonalities. Why? Because multiple sentences go through the same subsequences, the same subpaths. So you can have several sentences that partially align themselves along those several vertices of the graph, and then they go each their own ways. Some may join them along the way, and some may leave in between. This is a complicated diagram because it's actually a very faithful quantitative snapshot of what's going on in a particular corpus in which we keep track of each sequence. So the paths are colored because we know their identity. That's how we keep our database. By the way, the algorithm I'm describing is batch. So we have to have the entire corpus, in the current version, the entire corpus at the same time. So we proceed by looking at those alignments in a specific way. We start with the begin node and end at the end node, and look along the way at what we call a search path. So this is just one specific path taken from that graph, which we use to test for possible partial alignments. And as we go along from one node to the next, we look around, so to speak, and we try to find those alignments. So here you can see that intuitively, some kind of a bundle comes into being between nodes 2 and 3, maybe even 4. It comes into being because some paths join here, and then they stay together until the bundle is disbanded pretty much here. And the crucial issue here so far is just intuition, saying that probably you'll find sequences that you can align partially. But the crucial technical thing here is illustrated on this graph, where you see plotted a probability. Essentially, those are conditional probabilities of paths having passed through some nodes to arrive at some other nodes. So all those probabilities expressed here in blue, P of E1, P of E2, are actually conditional probabilities, but I hid the notation from you so as not to make this diagram more cumbersome than it already is. It's pretty cumbersome. So what happens is we can quantify basically by counting the number of paths that go through E1, what's the probability, the total probability of ever passing in that corpus, of ever passing through E1. Then we can ask for E2, what's the probability of getting to E2 having passed through E1. And that's what those probabilities signify. And we plot them. This blue dashed curve essentially shows the value. Faithful for this particular example, you can actually count the paths here, look at the numbers. N is the total number of sentences in the corpus. We can count what's going on and figure out that by the time we get to E3, the probability is 1, and it stays at 1 at E4, and then it goes down precipitously. And that's what we see as a sign, as a possible sign for the end, the disbanding of the bundle here at this point. And you can see indeed that many paths here leave this test, the search path that goes from begin to end here. We can do the same kind, yeah.
Yeah, I just want to see if I can paraphrase what you've said so far, because as you said, it's a complicated diagram. So tell me if this is right. In every sentence, you're looking for its substrings, which appear commonly, but if you extended them by one word, they wouldn't appear commonly anymore. Is that right?
Yeah, for that you'd have to look at subsequent, yeah. To find this fall-off, you have indeed to look at two vertices, so indeed, absolutely true.
Right, so in every sentence you want to find its maximal common end nodes.
Yeah.
Okay.
So the data structure for computing this looks just like a variable Markov window, which we move through the corpus depending on where we want to hypothesize the boundaries for this, because this can get very long. We don't want to look at the entire, 15 by 15 matrix. We may want to look only at 7 by 7 core of that matrix. So we do it going this way, but we also do it going the other way. And this is what the red curve shows. And again, the probabilities are just right here for this example. And we can ask the same question: where does the fall-off happen here? And we ask those questions in a principled manner. We can quantify. Essentially create a null hypothesis here that we test against the data, and then we can decide whether this fall-off is significant relative to the number of paths that are involved in this example. And the same in the accounting proceeding from the left to the right. So we have essentially a definition of a pattern. This is what we call a pattern. This bundle, the concept that I invoked informally of a bundle, we call it a pattern if in this context the probabilities of the paths remaining or leaving off satisfy the probabilistic criteria that I just alluded to. I'm not actually going to show the formulas because they're kind of beside the point. The important thing is that we do this accounting in the present context. So the probabilities are counted in a context-sensitive fashion. So we don't do something like compute the likelihood of the entire corpus given our grammar or candidate grammar and then work back from that. We work on probabilities in a very context-specific manner as described here. So the algorithm we refer to as adios, which is automatic, which stands for automatic distillation of structure. Now, once we found a candidate pattern, one that withstands the test of significance in context, we are ready to abstract it away. So we can take the sequence of nodes where a bundle, statistically significant bundle exists, and we rewire the original graph so as to make use of this new unit. This pattern P becomes a single node here, but notice that E2 and E3 and E4 don't go away. They remain there because they can be in the path of other sentences that are not subsumed by the decision to make a unit of this bundle. There is, in psychology, there is a process, I think, that corresponds precisely to this operation of making a unit out of a set, in this case a sequence of units. It's called, not surprisingly, unitization. So we call this a unit and we adduce it to the lexicon. This becomes a new entry in the lexicon. And there are two modes in which this can operate. We can, once we found that a pattern is significant in this context, we can replace it. We can rewire the graph in all other contexts or only in the context in which it is significant. So this is one major choice. Usually we stick in all the examples, well, all but one examples I'm going to show you. The rewiring is done in all other contexts. So this is kind of an almost promiscuous choice, but this is the only place where we are allowing ourselves to be that general. Basically, the algorithm is very, very conservative because, for one thing, the decision about pattern significance is done relative to the context in which the pattern is embedded. So because this pattern now becomes a new member of the lexicon, we essentially go recursive. This is what I mean here by saying it's a hierarchical abstraction, because now I can look for additional patterns using this newly extracted one as a new unit. So the abstraction is context sensitive and it's hierarchical. Patterns become units. Now, once we found, this is again a complicated diagram. Let's take the pictures here one by one. Here on the left top side, we see a pattern, took the something to, and we see a bunch of units here that are once removed from the original task path. Now, this bunch of units are about to become an equivalence class. Because, why? Because they are interchangeable in this context. We just found on the base of the corpus we have that table, in this example, table, chair, and bed are in some sense the same, in some sense equivalent, but only in the context of took the slot to, right? So this is an example in this of the sense in which we are conservative. We are not committing to anything like, we don't verify parts of speech. We don't say a noun would go here. I think it would be sticking our neck too far out to say a noun would go here. And that's the source of a lot of trouble for people who are trying to infer grammar from data. This kind of overcommitment that we don't do. And once we've decided that an equivalence class exists in a particular context, we can use it to attain what we call stack generalization, in which another equivalence class can be sought in the same context. Yeah?
How do you choose the context to do that?
Well, we essentially, the algorithm goes over all the paths and tries to find first the patterns and then the equivalence classes until it can find no significant candidate, at which point it stops. So it's kind of self-terminating. I have at the end, if someone is interested, I have some data on the computational complexity of this, so we can maybe get to that later. So once equivalence classes are found, obviously this makes for a lot of possible generalization. For example, any combination, if blue, red, and green are equivalent in this context, and table, chair, and bed are equivalent, then even if the blue bed was not a path in the original corpus, it now becomes one. So this, it's important to note, this is the only way in which we generalize. It may seem restrictive. If you ask, what new sentences can this algorithm accept? Can the resulting representation accept? Only those that are related to new ones by this process. And of course, the thing to realize here is that this whole thing is recursive. So in this example, the units here are individual words, but they could be, and they are indeed, complicated recursive patterns. So this generalization, which looks like not a lot, is actually quite a lot. Yeah?
Do you allow an equivalence class to grow so that maybe another time you have one more that appears and...
No, we are
so
being...
be a separate equivalence class.
Yes, and in fact, we'll see examples that precisely by virtue of being conservative and keeping maybe the same units in separate equivalence classes in different contexts, avoid the sin of overgeneralization. So let's see what those patterns look like. Since linguists like to look at trees upside down with a root in the air, this is one. And let me show you the trees that get abstracted away by taking you through a simple example, a path, an original sentence from a toy corpus produced by a grammar, which you'll see in a couple of minutes. George is working very far away. Actually, this point far away was realized as being a pattern of a fixed kind. Think of it as an idiom, kind of silly idiom. Far away just always hang together, so they became a pattern. And then in some later stage, another tree was grown here with far away being subsumed by it, and you can modify that by either choosing extremely or very, but not both. So, and this string got subsumed in a pattern here numbered 120 that gives you the choice of starting with any of those. This is an equivalence class underlined. This is our notation for the either Beth or Cindy or George or Jim or Joe, and then is, and then either celebrating or leaving. It's pretty silly grammar, and like the horse is living very far away, things like that. This is what it can produce. And finally, in this case, a single pattern remained on the path from begin to end, and this is like an S production in the grammar. So here's a grammar rushing in from the left side. So S goes to begin, following by P144. It's this one here, followed by and. And how about P66 is the word is followed by E65. It's this one here, is followed by anything out of this collection. And that's how things look like. So they do look like trees. And something we haven't done yet is we haven't yet had a proper look making sense of this forest and compare it to what one would expect just by having read a linguistics textbook. And I think it's important to do that. We haven't done that yet. Now, let me show you just one example of structure-dependent generalization. Here's one of those silly sentences produced by that same grammar, which you'll see again in a sec. Beth thinks that Jim barks and the cat flies, doesn't she? So doesn't she fits Beth here, right? So the grammar, this is a toy grammar that was made so as to realize that Beth is female and agrees with the gender of the pronoun here. And look what happens when a corpus containing sentences precisely like this one. In fact, this is one. These are not, by the way, fanciful diagrams. These are actually reports generated by MATLAB automatically from the patterns inferred from the corpus. So to enforce this agreement that spans all the way from here to here, the system decides that there should be an equivalence class that contains Beth, Cindy, and Pam. and it's distinct from the equivalence class that contains Beth, Cindy, Pam, and then some male proper nouns. And that's how this agreement between doesn't she and Beth here is enforced. Well, it's enforced, it has been essentially discovered by the algorithm. We didn't force it on the algorithm as such. It wasn't built into the system. And you can see the form of the rules here, if you want to translate those trees into rules, it would say, so what's the difference between P55 and P84? Well, the difference is that this sits next to begin, it's at the beginning of the sentence. So the production would look like begin followed by P55. It goes into begin followed by E56, followed by things, followed by that. So it's kind of a context-sensitive way of, well, a standard context-sensitive rule representing this tree here. So now let's see some evaluation of how this thing works for some standard benchmarks. This is this grammar, this target grammar on the left is the one you'll find in a recent paper on grammar in grammatical inference by Adrians and Verfort. And they have an algorithm which has been in development for some years now, Emil. This is version number 4.1 that was in this paper described, applied to this grammar. This grammar has 7 rules, you see them here, and 29 terminals. Emil version 4.1 inferred, we are not told exactly how many, but between 3,000 and 4,000 rules. Yeah.
I don't understand something. Are you claiming that there was a natural corpus from which you extracted it?
From which we extracted what?
The grammar.
Oh no, this is a made-up grammar that was used to create a corpus, from which then Emil extracted something and we extracted something else, which I'm about to describe.
I thought we were going to prove Chomsky wrong, and that's.
I didn't. Did I say that? No, I said that. No.
Let's say you said it. I said I thought it.
No. I'm going to show you some. This is a toy example. Well, relatively toy example. Now I'm going to show you performance on some less toy examples. Okay. Well, this may be toy. I mean, it certainly looks like not a very big grammar, but look at where one of the best algorithms for grammatical inference is. And we end with 28 patterns and 9 equivalence classes, and we have 100 precision and 99% recall on a corpus generated by that grammar. So these are some of the equivalence classes that these are all of the equivalence classes we find from a corpus generated by this grammar. And almost all they are put into one-to-one correspondence with what you see here. You find that this class knows, likes, Mrs. C's actually corresponds precisely to this equivalence class knows, likes, Mrs. C. Some things are missing here, but they actually appear, they got incorporated into the bunch of patterns that you see here. They just couldn't fit on the same page. So we are somewhat promiscuous in the way we add new patterns to the lexicon, but not too much. I think it's a reasonable price to pay for this kind of performance. Having your representation have, instead of just 7 rules, have 50 rules. It's okay with us. Yes.
So these subscripts A and P, is that animate and not animate?
In the original grammar, yes.
Yes.
I guess so, yeah.
Right. So you're requiring it to learn that distinction.
Well,
and from your precision numbers, we can see into that.
Let's see, let me try to go back. Yeah. So John and Mary are together, but house and shop are separately together from John and Mary. Okay, so I guess in some sense, yeah.
Yes.
So the shop actually got incorporated into many of those patterns, which maybe some post-processing could save you a few bits on, but we don't really care about that. So that's a toy example. This is a less toy, well, somewhat less simple, yeah.
When you say precision and recall, you mean unlabeled brackets?
No brackets. This is surface, this is just weak generativity. Okay? Sentences produced by this versus sentences produced by that. Kind of symmetrical difference. So this is the grammar that produces those silly sentences about the horse living very far away and Beth not believing that the horse is actually doing that. You see the entire grammar here, it's 28 rules, 50 terminals, and this is one possible sentence, that the cat is eager to please, disturbs the cow, and Joe and Cindy think that Pam believes that George thinks that the rabbit barks and the dog meows, don't they? It's of course a nice agreement between don't they and Joe and Cindy. And here's a performance plot that shows several things at the same time. So first, this diamond sign here it is. So this is precision and recall as I just defined, right? This is surface, just weak generativity. On a corpus of 200 sentences. It's the grammar you just saw with up to 10 levels of recursion. There's actually a recursive, I think at least one recursive, certainly one recursive rule there. So the sentences can get really cumbersome. So we allow up to 10 levels of recursion. We run it to generate 200 sentences. We feed those to the algorithm and we get 80% recall and about 80% precision. If we only, this is what I called earlier the context-free mode. If we allow a pattern just discovered to be only rewired in the context where it was significant, that's what we call the context-sensitive mode, the precision goes all the way up to almost perfect. The recall suffers a tiny bit. So this is the context-sensitive mode. Mode A, the black dots here, is when we start with no spaces. So it has to bootstrap itself to find words before it finds phrases, patterns and equivalence classes. So with just 200 sentences, the precision is pretty good. The recall is abysmal. And by the time it gets 10,000 sentences, it's almost here. So we need much more data to bootstrap ourselves from just characters. Now this would work. This works for characters in text. This would work for any symbolic data. So if you have some symbolic representation of a sequence of whatever sounds in speech, I guess if you throw it a sufficient amount of data, it would do kind of almost the same way. There's one mode which I haven't mentioned as yet here. It's this one. We call it semantically supervised, which is our way of saying when we hand the would-be equivalence classes to the algorithm on the plate, that's how it does. So it basically allows for a faster learning, and it gets with the same number of training centers, the same size of the training corpus, up to this point on recall and precision, whereas the standard mode, which we use for all the subsequent examples that I'm going to show, only gets up to about this point.
So for semantically supervised, when you hand it the equivalence classes, is this only the level 1 equivalence classes? Equivalence classes of words, or?
Of words. We tell it which like cow, dog, and cat are the same.
Yeah, okay. And you don't go any higher?
No,
okay.
Right. So now a slightly more, or maybe a considerably more complicated input corpus. This is the ATIS input corpus, what do you call it, air traffic information system. There is a handcrafted context-free grammar for that corpus, which has about 4,500 rules. And these are the patterns that we find by training our algorithm on that natural language corpus. So this is real as opposed to the toy natural language coming from human speakers. And some of the sentences that can be generated here or described by these patterns, I would like to, this is obligatory, and then one of these, take, for example, the air, or I would like to book the first class, something like that. And you can see, you can look at the other trees here and see that this is your typical kind of sentence you find in the context of trying to book an air reservation. The numbers here at the top correspond to the degree of generalization afforded by each of those patterns. So this one can generate 10 sentences, as many as are actually present in the training corpus, subsumed by that pattern. Here the generalization is not as strong, but in some cases, some patterns, not in this particular set, generalize by a factor of 100 or sometimes 1,000 when those are really deep and multiple choices are allowed at multiple levels. So when we run the learning algorithm on the ATIS corpus with different values of our parameters, this gives me the opportunity to tell you what the parameters are. We get differing results. The algorithm has basically 3 parameters. one has to do with, actually two have to do with the definition of a significant drop in the probability in that diagram that you saw in the beginning. And one, the remaining third parameter, is the window, what is called here L, the window within which we allow paths to diverge and then converge back again to search for an equivalence class. And as you can see, the value of L has a strong influence on the results. This can be related, it's an interesting issue. It's kind of like almost attention span for sequences. If you open your attention window too wide, you're getting maybe better on recall, but poor on precision because you allow too much of a freedom too early on and so on. So there is an exploration here which basically contains the message I want you to take home from this, which is when we set this window parameter to a value between 5 and 6, we get about between 70 and 80% both precision and recall, learning from a corpus of 120 sentences from this Attis collection. Now, there is one thing to note here, and this is the number of learners. And I have to explain what this means. The algorithm is greedy, so a pattern learned or an equivalence class learned is never released back into the wild. So there's no undoing any wrongs we've done. They just stay with us. And that's what makes the approach dependent on the order of so the order in which the sentences in the corpus are numbered, not presentation, because it's a batch algorithm. So to counter that in a silly way, we just run multiple learners, and we ask for some kind of basic agreement between the learners as to the acceptance and the generation of sentences. So the best result here was produced by a cohort of 150 learners. And it's an interesting issue that we can take on and then think and talk about its cognitive plausibility, but it's a separate one from the description of the algorithm. For better or for worse, we are greedy and batch right now. Now, so I want to raise the question. Jason, you want to say something?
Yeah, just a question about L.
Yeah.
Is that being measured in words or in constituents?
It's being measured for the current task path, and initially it's words, but later on it's not. Right?
Yes. So it seems quite high, actually.
Yeah, and it has an interesting, yes, 5 or 6 sounds like a lot.
Yeah.
Which means actually that one way to see it, you can say we can tolerate quite a lot of divergence in the way when used with this way of defining significance, right? So we can look at pretty wide windows. Paths can go away and come and return.
Yeah, I mean, it seems like maybe this would show up if you have what blah 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 for, and you want to be able to correlate those even before you come up with some kind of analysis of the internal structure.
Well, I think it doesn't. So the way I like to think about this is in terms of, just to anticipate myself for later, especially since I'm probably going to run out of time.
Sorry.
Not your fault, it's my fault. We like to think of representing, of enforcing those long-range agreement things locally, which is precisely what people who work within the tree joining grammar formalism try to do. So we would actually be happier if we could work with smaller value of L in that sense. But it's one of those topics that need to be explored, and we'd love to explore it later on. Yeah. So how should one evaluate a system that tries to learn not from a toy corpus for which we have a grammar, but from a natural language corpus for which we don't have a grammar? You may think that you have one, but I'll be willing to argue with you about that. So a standard language acquisition scenario: a teacher who knows or that knows some grammar, a student who learns some grammar, and you test by comparing derivation trees. That's what strong generativity is supposed to be about. But there is a problem here. The problem basically is that those derivations are stipulated, right? Here's a tree, take it or leave it. It's in a tree bank and it's there for all eternity. It's often disputed by the linguists themselves. It's never actually observed, so no one saw a tree growing in someone's brain ever. So G0 is inaccessible. Even if it were accessible, the equivalence is kind of undecidable. So it's asking, is G0 like G? Is it equivalent to G? It's a bit difficult to answer. So what we propose to do, as a temporary stopgap measure, we don't say that we are happy about that, because obviously language is about structure of those strings, right? Not just about the sequence. But for now, we don't see a better resort than to use surface data from human subjects. So for example, we have the model, as we'll see in a sec, undergo language testing, and we also have subjects rate the output of the model. So taking sentences from the ATIS natural language corpus, giving them to subjects and asking the subjects to rate the acceptability, we get about 70%. This is this bar. Taking sentences generated by the grammar we learn from the ATIS natural language corpus, we get about the same level of acceptability. So subjects on the average don't think that, they don't know of course, sentences generated by our representation are any worse or better than those in the actual ATIS corpus. Now, I'm sure that most of you realize that when you use the ATIS context-free grammar in a generative mode, you get basically junk out of the grammar. The figures differ depending on, I guess, whether or not you throw in some probabilities, but basically the grammar is not good as a generative one, which kind of misses the whole point, right? Because you want to be generative. The whole enterprise is supposed to be generative. So we try to test ourselves as best as we can using the knowledge, the information that we have access to. So another way of evaluating the model is by making it take tests of, this happens to be, this forced choice set of questions happens to be taken from an English as second language, a standard test that is taken by probably tens of thousands of students in Sweden. It has the advantage that you don't have to pay $500 for it, so you can find it on the web. Many, if not most of the other tests you have to pay for your nose to get. This one you can download. So the pilot slot looks wide, isn't, doesn't, or don't. You have to choose. So basically we have a way of evaluating each of the three possible choices here. The pilot isn't look wide, the pilot doesn't look wide, or the pilot don't look wide. Actually, there's some indeterminacy here. In some communities, that would be, the third choice would be acceptable. And we essentially apply our algorithm to this test. And there is some technicalities as to how we do it. How essentially the idea is to get our patterns activated to different degrees by the input. And we can do it even when there is pretty little overlap between the vocabularies. And I'll skip all of this. I'll just show you some bottom line here. And the bottom line is produced by a version of the ADIOS system trained on children-directed language. I think a corpus of about 3 million words. And we get it to perform at about 60%, 58, 57% precision and recall on that English as second language test, which is about the level of performance you expect from a ninth grader in Sweden. Which is, as far as those approaches of grammar acquisition work, it's fine as a first step, I think. It's not bad. Surprisingly, pretty much the same set of numbers we get from many other grammaticality judgment tests. All of them, it's the same instance of the ADIOS representation, the one trained on childs, used here in different contexts. Now, we also tried, with some degree of success, to apply this method to different languages. And the corpora we used for that is the Parallel Bible, again, something you find for free on the web. And we applied it to Chinese, Spanish, the entire Bible, all the books. I think 66 books, if I'm not mistaken. Spanish, French, English, Swedish, and Danish. And what you see here is a diagram that looks at what we call the pattern spectra. So this is like a histogram with, say, TT being a sequence of two terminals. You just scan all your collection of patterns and you look for, just count the number of occurrences of T followed by T, terminal followed by terminal. You can do the same for T followed by T followed by T. So this is like a simple collocation between two words. This is a collocation between three words. And there are other possibilities here. P standing for pattern, T standing for terminal and E standing for equivalence class. It's just a way of getting a snapshot of a language. All of a language, or at least everything that goes into the Bible, onto the screen. And you get certainly some correlations here. So collocations are very frequent in all those languages. Triple collocations are frequent and so on. And when we run some clustering on this set of similarities, we get this dendrogram. So we get Spanish as being the closest in this space to French, and then to English, and then Swedish and Danish, and Chinese is here all alone because it's all alone up there. So
are there only patterns of length 3, or is that just?
we went up to length 3, yeah.
So this is probably maybe about just about the conventions about where spaces are put.
No, because
there may be more phrasal verbs in some of these languages than others, and that would affect whether you get TTT or not.
I don't think so. Well, for TTT, yes, but what about PPE? Like P can be a whole tree, can be hiding beneath it. So it's difficult I find it difficult to visualize what's going on there, but the tree looks kind of interesting intuitively. So this is the alternative framework. I mean, alternative to, I guess, to an attempt to squeeze your grammar into to learn it, and then to obtain at the end of the day a grammar that is really, really concise in some manner, in some sense. I came across this quote from Langacare actually pretty late on in this project, but it's very much applicable, I think, to what we are trying to do. In the present framework, the grammar is simply an inventory of linguistic units. Of course, he doesn't, but we do specify what we mean by units. And then how he sees this process, Langacare in '87, writing in the Foundations of Cognitive Grammar, out of the sea of particularity, speakers extract whatever generalizations they can. Most of these are of limited scope. Some forms can be assimilated to any general patterns at all. You know, my favorite story about this is how someone went to look at all of the French language and found that no two verbs had precisely the same distributional patterns across all of French language. This is, I think, what I mean here. Fully general rules are not the expected case, but rather a special limiting case along a continuum that also embraces totally idiosyncratic forms, like completely spelled out patterns. And patterns, he actually uses the word patterns of all intermediate degrees of generality. And I guess this is a pretty good way to capture visually or cartoonishly this insight. No exceptions to every rule, except maybe that one, maybe not. So very quickly, some related ideas in linguistics. So Chomsky now, I guess, the way he puts things is language more like a snowflake or like a spine? Apparently he had some problems with his spine, and he went to see his doctor, and his doctor said, look, it's not just your spine, all spines are just a terrible mess. They are just so messy, biological structures. You don't want to go anywhere near them. So he says, I sympathize with him because sometimes I have to wear actually a girdle to keep my spine from collapsing. But it doesn't mean I don't appreciate my spine. You know, it does for me. So this is this way of looking at the world. Language is like a snowflake wedged between this is syntax wedged between semantics and phonetics or whatever. And it's this way. And then it's this way. You know, spines are great. They can support someone standing straight and holding a light up. So spines are a great thing to have. And we know that spines like this evolved on so many occasions. So why downplay the importance of something that actually can be evolved? So more seriously, of course, this idea of irregularities being central to syntax is what caused, I wasn't around, well, I was around, but not around in language. In 1970, this famous split, right? This wasn't it Lakoff's PhD dissertation that was titled Irregularity in Syntax? I think it was. And then a bunch of other people realizing that exceptions are a crucial part of language, how you capture linguistic knowledge, this I language. So we have in Langacare writing about inventories of units, Jack and Duff, certainly in '97, certainly more recently in 2002, idioms and semi-productive forms, prefabricated expressions, syntactic knots, frequent collocations, multi-word expressions, constructions. And I would place 3 joining grammars here as well, because if I have maybe a couple more minutes at the end, I'll show you how I can draw an analogy between certainly between the elementary trees of a tree joining grammar and the patterns that we find, but also, as you can imagine, is a direct counterpart to the operation of substitution, because that's what essentially pattern membership in another pattern means, and also adjoining. So we haven't gotten around to capturing, certainly the algorithm doesn't look for instances of adjoining as such, but a post-processing stage could find, I think, such instances. So I think tags actually belongs at least as much here as on the other side of the divide. And just to summarize, what we've done is an exercise in computational linguistics. We define, when my linguist friends come to ask me, what is it that you're learning? I say, I don't know, whatever our algorithm gives us. So we define this knowledge procedurally, algorithmically. So computational linguistics is crucial. Formal linguistics is crucial. We are deficient on that side because I haven't been able to persuade a real linguist really to talk to me for more than a few minutes at a time. Well, maybe one or two. And psycholinguistics is important because it's so important because we don't have direct access to the I knowledge, the grammars that people have in their heads. We have to use some more roundabout ways of querying them for extracting the syntactic nuts out of their hands. And that, of course, takes some psycholinguistic research. That's it. That's the planned part. I have some extra stuff for you if you call for it, if I'm not really out of time later on. Thanks for your attention.
Tell me again how you encode the level of generality that patterns have so as to be able to express everything from idioms to schemas that are totally general to the language.
Well, I guess totally general schemas is the extreme we never get to. We always, so in this sense, this is, if you think of this as a grammar, it's lexicalized. It's always anchored at least at in one lexical item. But it certainly can vary from just the collocation between two lexical original lexical items that just hang together because that's what the corpus warrants, and something that has maybe a couple of, or maybe just one original lexical items and all the rest being those recursive tree structures. So does that address what you're asking? So we don't, one parallel actually, which I forgot to mention to kind of cognitive linguistics is to construction grammar, except people like Adele Goldberg, they write and talk about say the passive construction, which is completely abstract. So you can take any verb and plug it into. We don't get that. So we are we stop one step short of that complete generality.
But other than that extreme, you can cover the spectrum from totally idiomatic to more general.
Right. Including, in fact, many idioms they have movable parts. You can insert something in between. In some you cannot, but in some you can. So we can account for that by essentially having a completely spelled out the idiomatic part with an interposing pattern that allows some free variation in between.
I was wondering what exactly you meant when you said, with respect, just to make a sort of throwaway comment about if you induce a grammar, how could you tell if it was the same as the teacher's grammar? You said that was undecidable. I was wondering what exactly you meant by that.
Well, I just remember from my computer science days that the equivalence of context-free grammars is undecidable.
Well, the equivalence of context-free languages, the equivalence of of one grammar to another in terms of the set of strings that it generates is undecidable. But the equivalence of the set of structure, if you would demand strong equivalence, then that it's easy.
Then I guess it's somewhat of a tangential shot in that case, yeah.
But I was wondering, the one observation that one makes immediately observing the kinds of structures that you get is that they tend to be quite flat. In a way that, as you saw in the cases where, some of these noun phrases just instead of getting put in with the other nouns, they got just integrated directly into some other rule.
Mhm.
And I was wondering whether, is there some parameter of the, if you play with the parameters of, well, I guess you said that you had to have this test of statistical significance of whether such a pattern was a sort of distinct pattern. But have you played with varying what that criterion is and whether that affects the resulting length of the pattern?
This L parameter, the window parameter, affects a lot the depth. Now, I want to say something about whether those things look flat or not. I guess in minimalism these days, you get really deep trees that I think are deep for a reason that has nothing to do with anything apart from someone's intuition.
Sure.
So, we certainly do get trees that are 5 or 6 or 7 levels deep.
Right.
They're kind of balanced, which I kind of like, but yeah, but that's why I say
Well, one of the reasons I'm asking this is because there are other things that are conditioned by hierarchical structure other than just getting the words right. So things about conditions on anaphora or conditions on scope or things of this sort. And they seem to be conditioned by relative hierarchy, certain kinds of configurational properties that aren't at least going to be transparently represented. I mean, depending on what exactly the structure turns out to be, it may or may not have the kind of necessary hierarchical asymmetries. So, and linguists sometimes use, rather than just using distributional arguments to argue for certain kinds of constituency, also use things about anaphora or tests of this sort in order to say, well, this thing must have a certain kind of hierarchical asymmetry in order to account for this relationship.
Right. I absolutely agree. I mean, I cannot disagree honestly with the need to account for a whole bunch of results, of which anaphora is one. But I would want to go for the bottom line. I would want to ask, is this set of representations good for the bottom line? And I would have, it's up to me, the onus is on me to devise a task that would just take a bunch of test cases, just as we did with the ESL test, and see if we do like 90% right, I would be pretty happy with that. Without forcing trees, without it happening because the trees look right to someone, right?
Right. No, sure.
Because if you want co-reference, the right kind of co-reference, the question is, do those representations have enough information? It's an absolutely valid question.
Yeah.
I would love to know the answer. I don't know the answer yet. But that's how I'd like to approach it.
Well, certainly they have enough information. The question is whether the regularities are going to be sort of transparently represented in the kind of representations that are induced.
Right. So, I've been, as you saw, I quoted from Chomsky 2004. I was really impressed by the clear way in which in that interview he laid down what he thinks are interesting things about language. I don't think they are necessarily interesting, but I think they are absolutely valid. I mean, if one finds a particular pattern, especially across languages, in which things behave, according to which things behave, I have to account for that, right? I need help.
What about relatively free word order languages?
Right.
And you looked at the Bible, a couple of languages, but it's such a special genre that it may not be representative of natural speech, right?
Right.
So how do you deal with that problem?
Well, we don't know. We haven't tried things like Russian, which we should probably have, because in Chinese I cannot tell you anything about the outcome, but in Russian I could, but we haven't tried it yet. Yeah. I expect that we pay a price for maybe in the sense of doing separately. You do have occasions on which word order is used, even in languages like Russian or Latin. We would just have to multiply things times however many is necessary to capture the regularities while adhering within each pattern to a particular word order. I don't know how steep the price would be, right? I can tell you though that I tell you what's the price I'm willing to pay, right? So if I have a say 50,000 word lexicon in English, if you admit that about me, I happen also to have about the same number of words in Hebrew and in Russian. So if you only know English, you can afford. I can afford another addition to your lexicon of 100,000 units that can be, as complicated as that. Because a word doesn't come cheap. What's a word in a lexicon? It carries enormous baggage, cognitively speaking, right? So it's not like words are simple and patterns are complex, right? So it's a question of price. Question is, can we settle on the price? We'll see.
Word-to-word relations in those languages that you already alluded to, where word order is discrete, are expressed by inflectional information.
Mhm.
So it's conceivable you could convert from one to the other and back.
So-
So the inflection tells you what kind of relation something has to the verb, which would say if it has nominative case, then it would be the same as
Right.
the word occurring before the verb in a language that has a fixed word order. So it's
And the morphology is really nasty. For example, if intonation is important, or if the patterns happen to be, like the vowels in Hebrew or Arabic are interdigitated with the consonants of the stem, we'd be in more of a trouble. The question is, can we survive that? I don't know yet.
So if you wanted to summarize in one sentence or so, what you have that Zoe Harris didn't have, what would it be?
No, it's actually it's surprisingly easy to answer. It's the criterion for significance. It's the safety. It's the criterion that allows us to generalize just enough to be on the safe side of things. So safety first. And of course, we can actually play. We could play with those. We could twiddle the parameters ad libitum, which is, if you remember the 1950s computers, you couldn't do very easily. So. Harris was fantastic in his insights, and now we have the tools to put that into practice.
So this is an obvious question that you didn't talk about, which is recursion. So do you ever merge a category with one of its subcategories?
We don't, but this is what, let me try to go forward and see if, come on. So this is a standard diagram showing a joining in a tree joining grammar, and I try to express here in terms of our patterns and equivalence classes the relationships that would allow me to claim that this thing is adjoinable to that one and so on. So this needs to be, in principle, it can be discovered by a subsequent stage looking at the patterns already extracted. And in fact, I have a student now trying to do just that, but we don't have any results about that yet. So we don't have. So right now, we are taking care of that recursion that I mentioned, for example, in that toy grammar that had up to 10 levels of recursion. We take care of that by just growing deeper trees, right? And by basically by multiplying trees. But maybe we can save on that a bit if and when we have this mechanism in place. We don't have it yet.
This is, I guess, an example of a more general question, or you would think of it as an example of a more general question, which is, given the output of your system, how would you clean it up? In order to get trees which are correspond.
Absolutely.
Sorry, which preserve the generalizations that linguists point out.
Absolutely.
Because otherwise, you don't have any theory about why languages are sort of as well organized as they are. Despite the fact that we can learn all these idiosyncrasies, some people would argue, maybe they're wrong, that there's more internal structure in some of the constructions that you find have a lot in common.
Absolutely. So what I need is a combination of tools like you're using, like Bob is using to look at. He looks at say those elementary trees, if I understand him right, trying to find commonalities and maybe map some trees onto others and find simpler sources for what looks like a larger forest. And you do similar, you did for your previous work, similar things. So that needs to be done. So this forest needs to be looked at.
Could you put the Chomsky quote on?
No, wait. We're just looking forward to you taking issue with it.
I look, well, okay.
Isn't it on the first slide?
It is, yeah, but I'm not using Microsoft. I'm using actually a beta version of OpenOffice. I'm willing to pay the price, but
Now we're paying. I see. So what's your comment on this?
Bollocks.
I see. And when you say this comment, is it related to what you lectured us on?
This comment?
No, you just said balls.
Oh,
And I'm wondering whether your comment is related to what you, to the lecture you just gave.
well, I think this is, well, it's a question of judgment. Does any procedural approach get you anywhere beyond morphemes? I think it does. So yes. What do you think?
Yes, he does. I mean, I don't believe this.
Well, I bet Chomsky would argue, no, what you've just shown is I mean, you're embracing the conclusion that all the generalizations that one wants to get are fantasy, right? That in fact, and because exactly the kind of question I guess Jason was talking about, where you have recursion, when you have these 10 levels of embedding, each of the sentence with 10 levels of embedding is treated differently from the one with 9, is treated differently from the one with 8. And Chomsky would say, well, that's just the point. You've missed an enormous amount of generalization that's there. And
But that's the question is just the mere, you know, let me cede the floor to Steve Pinker and Ray Jackendorf, who just published a paper that takes on this science paper from last year by Hauser, Fitch, and Chomsky about how recursion is all there is. It's snowflake, and it's all recursion. They just disassemble. They don't leave a single stone standing in that argument. If that paper doesn't convince you that language is like a spine, you know, nothing will. Okay, it might be the case, but I think they make the case much more eloquently than I can by also looking at, you know, Jackendorf he may not be counted by some extreme people as a linguist anymore, but he still is deeply rooted in that community, and Pinker is as well placed as any for talking about evolution. So I defer to them on that.
I think that's not the point. I mean, the question isn't whether you take Chomsky's position that all there is recursion, that's all there is in special language. But there are lots of generalizations that the representations you have aren't capturing without some amount of post-processing.
And that's what I meant by when I told you earlier in this private conversation we had, by asking. I'm going around asking people for a prioritized list of phenomena that need to be accounted for. Mere recursion, just the beauty of the trees is not one of them, right?
No, absolutely.
It's not one of them, but many are, and I want to be told, and I want to go ahead and try to see if it fits for size.